let's see how to solve the very first part, the transient part of the solution. Here I just copied the homogeneous equation. V dot is equal to minus 0.05V. This is the homogeneous equation. But now I put the index TR, so VTR dot is equal to minus 0.05 VTR, because the homogeneous equation is valid for the transient part of the solution. And now we are going to define the formula of VTR. VTR is a time function, VTR of t, and it is equal to me to the power of lambda t. So it's a kind of exponential function. It is usually an exponential function. So why do we have an exponential function? I am going to prepare a separate video about that. So now let's say it's a definition. VTR is me to the power of lambda t. But what is m and what is lambda? M is a constant. It is not determined in this stage. We are going to define the value of m at the very last step of the solution. So m is now undefined. So m is just a real number. So the value is from minus infinity to plus infinity, any value it can have. This is why the solution is general, because m is not defined, but the value of lambda is defined at this stage, and lambda is called the eigenvalue of the system. So we are going to use the definition of eigenvalue for the lambda. So now I'm going to put this general solution to this equation, and we can write the following: d over dt m e to the power of lambda t is equal to minus 0.05 m e to the power of lambda t. This is the equation we have. The time derivative of the exponential function is itself and multiplied by the time derivative of lambda t, which is lambda. So the left hand side is m, I put lambda 2 here, e to the power of lambda t, and it is minus 0.05 m e to the power of lambda t. And as you can see, m e to the power of lambda t can be found on the left hand side and on the right hand side, so we can cancel them like this one, and we get lambda, equal to minus 0.05. And finally, this is the solution of this equation. Lambda is equal to minus 0.05. In general, if we would have not only first order system, but second or third or more, so a higher order system, we would get the following: phi of lambda is equal to lambda plus 0.05, and it is equal to 0. This is the general solution. Phi lambda has the name of the characteristic polynomial. Polynomial. So we are going to denote the characteristic polynomial by phi lambda. Please remember it, because we are going to use it many times. So the characteristic polynomial is lambda plus 0.05. This is the polynomial. And if we set it equal to 0, we are going to get the characteristic equation. And this equation is usually equal to 0, and it's usually a polynomial equation. So from this polynomial equation, we have all the eigenvalues, and now we we are lucky because we only have a very simple equation, lambda plus 0.05 is equal to 0, and from this, lambda is a negative 0.05. So in other cases, this characteristic equation must be solved in a way. So as we can see that our general solution, I put it to here. So the transient part is m e to the power of minus 0.05. M is undefined. M is undefined, so this solution can be like this one, can be like this one, or with negative m this one, or this one. So this is for m1, this is for m2, this is for m3, and so on. What the value of m is, we don't know it yet, because we need the stationary solution to define m. So we are going to come back for the value of m at the last step of the solution. Now we have to stop here. This is the general solution, general because m is undefined, and this is the transient solution of our problem. So next, we are going to define the stationary state.